All right, so now we know what a separating hyperplane is, and we also know how to compute the distance of a point from a hyperplane. Now, the next thing that's left for us to determine is the thickness of a separating hyperplane. And the thickness is also termed as the margin. Thickness is nothing but the margin. And let me denote it by a gamma, which is a function of my h, right? And so think about it. This is like the distance from h, which is my hyperplane, h is my hyperplane, to the closest data point, and maybe like twice that. If you remember, like let's say we had these data points, and this is my hyperplane, and let's say this was my separating hyperplane, then by thickness, I mean that I should, the moment I try to determine the thickness, right, it should be twice the distance, because it has to be like on both sides. It has to be twice the distance from this point that it hits first, right? So distance from this edge, which is my separating hyperplane, to the closest data point. And that's what and twice of that, of course. And that I'm defining it as like gamma h. So now we need to understand what is this, and how should we try to find it. Now the good thing is that we have figured how to find like these distances from my hyperplane. I know how to find a distance of a point from a hyperplane, just like this dist equation, right? So we have this information already, dist x for any point n to a hyperplane, and we've seen that in the previous video. Now, like if we're considering all these distances, which one will impact my thickness? Well, my thickness or my fatness, whatever you like to call it, is impacted by that one point that is the nearest, or one or two or whatever like number of points that are the nearest, because beyond that I don't care. My thickness will be determined by that, by that particular point, or those set of points. And so that's why my thickness, which is my gamma of h, is going to be the minimum over all points n, the minimum of the distance, correct? And what is my distance in itself? So basically what I'm trying to figure out is the minimum over all points n, and by definition we already have this with us, which is w transpose xn plus b, the absolute value over the norm of this. Okay. And because this term here, the denominator, does not depend on xn directly, so we can also rewrite it as something like this: minimum over all points w transpose xn plus b. All right. Now we'll do a little bit of manipulation here, depending on what we already know about a separating hyperplane. The first thing that we know about a separating hyperplane is this thing, like the definition. I'm just like talking about the definition of a separating hyperplane was minimum over all points yn w transpose xn plus b equals 1. All right. Now we can like rewrite it, given that like everything is positive, so I can say minimum of n, the absolute value yn w transpose xn plus b, right, equals 1, right? Or if we just separate these, like my yn for a classification problem is like +1 -1, and so this could be like the absolute value is going to be 1 anyways. And so this becomes like min over all n, and the absolute value w transpose xn plus b equals 1. Okay, so as you can see, like this thing here is the same, sorry, not including the right hand side, just like this part here, the left hand side is the same as this thing in my definition of my thickness or my margin, right? So now we also see that why we need the definition for separating the data, because like simplifies the definition of thickness. And what is like my thickness is gamma h, is like the exact distance from the hyperplane to the closest point, right? And we already have some information about that closest point because we defined it in a certain way, like we define our hyperplane in a certain way, and so we can utilize that information here, the separating hyperplane. And so utilizing that equation, like this information, my gamma of h, if I just like substitute this there, I'm just like substituting this value in my equation, all I'll get is 1 over the weights, the norm of the weights. All right, so here it is. The thickness or the margin of a hyperplane is 1 over the norm of the weights of the separating hyperplane, right? That's what this is. And so this definition here is the thickness or margin. This is what we've been talking about until now. All right, so we have three definitions. The first one is the separating hyperplane, which is like the min of n over like yn, this thing. This is my equation of the separating hyperplane. Then the second thing we have is the distance of a point to the hyperplane, which we defined as like dist hx, which is given by w transpose x plus b over this. All right, so all these three definitions are important when we are trying to determine the thickness of the hyperplane. But when we're just like looking at only the final formula sort of that we arrived at, we are looking at it and we see that this thickness of the hyperplane depends on the weights only, right? And so think about like if there was no data set, if I didn't have any data set, right, this thickness will be infinite. Right? What does this thickness mean then? There is no thickness if there is no data. So then obviously it has to depend in some ways on my data as well. But I don't see that explicitly here in my equation, the dependence on data. Well, I can say it's implicitly there. It's embedded in the notion of my separation, like this separating hyperplane. And that's why we utilize that when we derive my gamma of h. So the separating hyperplane has this thing embedded in itself that takes care of the dependence on the data. So these weights are like the weights that satisfy this constraint is that like they should separate the data, right? That is important. So these are the weights whose like norm I'll be calculating, but they are the ones that separate the data. So the data is there, right? Otherwise this is infinite. All right. So the task of finding the fattest hyperplane or the thickest hyperplane or the margin or the maximum margin or the largest margin, all of those are like the same thing, right? Is to find the separating hyperplane with the largest margin, right? And I've defined the thickness. Now I have to find that one hyperplane that has this like largest thickness, right? Largest thickness. So you can tell I can formulate an optimization problem here, and let me do that. So my problem here is to maximize this thickness, right? Subject to some constraint, and that constraint is that it has to be a separating hyperplane, and that constraint is subject to minimizing n yn w transpose xn plus b equals 1. Okay, let's put it in a more like mathematically convenient form that like we just like move around terms here and there, and conceptually nothing is going to change. Conceptually this is my optimization problem, but you can tell, people who've taken optimization courses, you can tell like there are certain things like this min in my constraint value and the way the objective function itself is defined that's like not as straightforward to solve, and so that's why we are like making things move a little bit, right? So if I say like instead of maximizing, I minimize like the inverse of this, or in the sense like, let me write it down. If I say I want to minimize this thing, right? It is the same thing as maximizing the reciprocal of this, right? Which in turn, and these are all equivalent, so that's why I'm using this arrow or whatever you like to call it, is equivalent to saying like minimize half of this, because you know that this doesn't really count, it's a constant, right? Or minimize the square of this, right? These are all equivalent because I'm just like minimizing, I'm only interested in this. But why am I putting it in this form? Because we have data, and that data is in a certain format, and we have certain techniques that work well in this format. And so that's why you must have seen like optimization problems are often converted to some other form, and we are doing that. So what I'm doing is minimize half of, and this thing by the way is nothing but w transpose w, right, in my better sort of vector notation, subject to again whatever my constraint was, minimize n yn w transpose xn plus b equals 1. All right. So this is my optimization problem, but I'm seeing this like min here in my constraint. And again, as I'm saying, when we are trying to use any standard solvers or when we're trying to like put it in some standard form, some standard optimization form, I know that this is going to create some issue, but we can consider like an alternate optimization problem with a slightly different constraint that kind of also encompasses this part. So what is that like alternate constraint? Well, how about if instead of this, right? If instead of saying like the minimum of yn w transpose xn plus b equals 1, I just like get rid of this minimum function or this minimum part and I say, how about w transpose xn plus b is greater than equal to 1, right? So of course, like I'm relaxing my constraint a bit. This is loose as compared to the original one. The original one is tight, right? But when we think about optimization, we think about the optimal solution, right? And what happens when I found the optimal weights? What happened at that point? So when at that point, like when I find the optimal solution, the constraints will become like equivalent. Like this will become optimal at the point when this is 1. But I'm also allowing the feasible set to be like larger than what it was, just to like get rid of this form, right? So as long as there are both positive and negative examples in the data, these are equivalent optimization problems. Like constraints are not equivalent exactly. One of them is looser than the other, but then this encompasses that loose constraint. This loose constraint encompasses that tight one in it. Okay, so the solution to both will be the same. Feasible set may be different, and this also goes back, and let me like rewrite this optimization problem. So the problem that we are trying to solve for finding the fattest or the thickest or the maximum margin hyperplane is this w transpose w subject to yn w transpose xn plus b greater than equal to 1. So this is my optimization problem that I'm trying to solve. All right. And this also goes back to our discussion when we were talking about regularization, when we figured that we needed to solve for that equality constraint, right? So we figured that that's all where I have to stop. I don't want to keep going down, but then I'm trying to encompass that using that budget regardless, right? So it's similar to that kind of a thing where I'm saying, okay, I can come up with a more like larger feasible set and then eventually go and find whatever I need to find. Okay, so then the question arises, this is my optimization problem. And what exactly do I need to find? Well, let me write it down here only, or maybe move to another slide. Maybe I'm like running short of slides, but that's fine. So this is my problem, and what exactly am I supposed to find? My variables in my optimization problem are, so variables in my optimization, I'm going to show you a very like a toy kind of an example to understand what this is. These are my weights and the bias. The second observation that I have from this problem is that objective function is quadratic. Okay, objective function is quadratic, and it's important from the perspective of optimization itself. Quadratic functions have certain set rules that we will utilize in order to solve them. Okay, and then we have linear inequality constraints and not equality constraints. So linear inequality constraints, all right. And whenever like all these conditions are met, then this is nothing but a QP or a quadratic program. So this is a quadratic optimization problem or quadratic program. In short, we call it QP. Okay, so how about we try to solve this QP with and find the optimal hyperplane for our toy example. If you remember one of the examples that we looked at earlier, and see like what do we mean when we are trying to find this like optimal hyperplane, right? So let me go and check that. If you remember, I had this like data which is like 0 0 2 2, right, 2 0 3 0. Okay, and y was, I think the first ones were minus minus and then they were plus plus. All right, so what are we trying to find here? In this problem, we are trying to find W1, W2, my bias, and I'm trying to minimize this thing, and let me rewrite it. So basically what I'm trying to minimize here, I'm trying to minimize half of, then this is a very simple problem. Of course, we won't encounter such problems in practice, but this is just like good to look at. And now if I'm looking at each of these lines, so basically using each of these lines here, these, I can formulate my constraints because I know that this is the form of my constraint, like yn multiplied by the w values times x. So x values are given to us, w's are the variables, plus the bias, right? And so have it greater than equal to 1. So I'll write it for each of the lines. That's exactly what I'm doing. Let me write it down here. So we'll have like minus b greater than equal to 1. That's my first equation. The second equation is minus 1, 2w1 plus 2w2 plus b greater than equal to 1. And then 1 times, because yn is 1. And so 2w1 plus b greater than equal to 1. And 1 times 3w1 plus b greater than equal to 1. So we have like these 4 equations, and we have our objective function. And what we have to do is, like, if we had like n data points, we can solve it like in a similar way. Of course, solving it manually is like almost impossible. But the book also talks about it. If you go and solve these equations, these set of equations, what you will get is w1 greater than equal to 1 and w2 less than equal to minus 1. Now we want to minimize the objective function, and so given this feasible set, we will select w1 equals 1 and w2 equals minus 1 and b equals minus 1, because this is like a solution that minimizes my objective function. And so I'm selecting this solution, and so therefore my h, fattest or thickest, right, because this is what I'm interested in, is the sign of w1 is 1, so x1 minus x2, because this is minus 2 minus 1, the bias, right? And what exactly is my gamma, my thickness? My thickness in this case is 1 over this, which I think is going to be square root of 2. All right. So now you can imagine, like, this is the fattest hyperplane. And what is the fattest hyperplane? Well, we talked about it earlier. And if this is my data, right, and there was like this point here and this point here, right? So I shouldn't have drawn a square there, right? Or maybe these are on the same line. Okay, so then that's fine. So the fattest one is going to hit the nearest points. And let's say these are the nearest points. This one, and this one. They are like simultaneously going to do that. Why is it like simultaneously going to do that? Because I'm like setting up my problem in such a way that this hyperplane will shift if that is not the case. So what I'm saying is the fattest hyperplane will hit both the positive and the negative points, which is like, let's say these are the negative points and these are the positive points, simultaneously, the nearest ones on either side. So we can consider like such data points as the one that are supporting my hyperplane, because my hyperplane will shift depending on where exactly they're like these lie. And that's what I'm trying to do. So like if you think about this like region, this fatness or this thickness, it is dependent on these nearest data points. It is dependent on the closest data points. And so this thickness, if you like, we got this like 1 over square root 2. So this here is 1 over square root 2. And so this is like 2 times that. And so that's why like you'll get 2, like just add them up again. So the whole point that I'm trying to make is that this thickness is dependent on where these 2 points lie. These points lie, the nearest points that are there. And these like are kind of supporting my hyperplane. These points are supporting my hyperplane, right? And so that's where the name comes, support vectors. And so these are support vectors because it's supporting my maximum margin hyperplane, right? And all right. So one question that arises, let's say there were like more data points here. So this is 1 and this is 2 and all, right? All of them. And so what happens like if we threw away these points that are like this one and this one and this one? Because like based on whatever I looked at right now, right? Everything is dependent on these nearest data points, right? So if I threw away those points, those extra points, would my optimal hyperplane change or not? That's the question. Uh, a short answer to that question is the optimal hyperplane will not change, because these are the supporting points are there. So all I need is my supporting points, and I don't really need the points that are not supporting it, right? So then the question arises, like, why do we even keep them? Like, do we even need these extra points, and are these redundant or not, right? And of course, to a certain extent, they are considered redundant. And to find this like optimal margin hyperplane, we can say it suffices to only have the support vectors, right? Other data in some sense is redundant. Indirectly, we are, if you think about this whole problem, this problem of finding support vectors in like the maximal margin hyperplane, we are indirectly identifying the most relevant data points, and those relevant data points are support vectors. Let me write it down. Those relevant data points are support vectors, and that's where the robustness of this model, that's where the robustness of this model comes into picture. This is why it is so robust. It's not going after each and every data point, and so in some ways it's like um, not going after the noise, right? And it has identified certain relevant points, and it is just like based on that coming up with this hyperplane. So that's why the robustness comes into picture in this model. All right, so all of that is good about support vectors. Next, what we have to find out is that this was a very like simple, or like a toy example rather, I would say, and we need to have some kind of a more, I would say, um, organized way of solving this problem, because this is like I cannot go and solve, like if I had like 100 such equations or 1,000 such equations, I cannot just like sit there and solve all of them by hand. So I need a more, I would say, principled approach to solving this problem, and that's what we're going to look at in the next video, where we'll talk about an algorithm for solving this quadratic program and why is it so important. So then see you in the next video.